Hi there, welcome to this video. My name is John. I provide mathematics tuition and support for A-level maths, A-level further maths, 6th term examination papers and mathematics admissions tests. Very warm welcome to this video. We're going to take a look at a problem that I've selected from one of the past papers for the mathematics admissions test. And in particular, it's the 2020 MAT that we're going to be taking a look at, and it's question 4. That we're going to be looking at in this video. So this is one of the more structured problems from the MAT. So if you are familiar with the MAT, you'll probably know by now that the first question on the MAT is a series of multiple choice problems. That doesn't make them easy, and it doesn't mean that you should guess the answers. You definitely still have to show you're working for those problems. But once you get to question 2 and onwards, then they're a bit more structured. So we're looking at one of the more structured problems. Now, with the MAT, it's important to realize that the MAT is an opportunity for you to show your understanding of mathematics, but also for you to demonstrate that you are able to take unfamiliar information and process that information and expand on that information. Okay, that you understand mathematics in enough detail to be able to do these things. That doesn't mean that you need to know everything. It just means that you need to understand that in mathematics, you don't need to have been told all of the properties of something before you can work with that thing. You need to know what that thing is through its definition. So in this particular example that we're going to be taking a look at, you're introduced to the idea of even functions and odd functions. You're given their definitions and that's it. And then you have to logically deduce some of the properties of even functions and odd functions. Okay? And that's important to recognize that that's how mathematics works. You define something, what something is, and then you logically deduce its properties. You don't need to have been told what the properties are. You have the means available to you to just do that yourself. And this is an opportunity for you to demonstrate that you get that you understand that. Because one of the big objections that I get from often from A-level students, and when I've done GCSE in the past and things like that as well, is that if somebody's presented with a new and unfamiliar concept, even though it's arguably very closely related to something that they're already kind of familiar with, they will still say, I've not been told about this. I've not been given any examples. I've not been shown how to solve problems involving this thing, because they're completely kind of missing the point. Okay, so for example, with factor theorem, it's very usual to get kind of used to just using the factor theorem on cubics, for example, at A level. Now, of course, many of you will realize that factor theorem applies to polynomials, all polynomials. It's so often used on cubics at A level that sometimes if I give somebody a quartic and suggest that they try to use factor theorem with it, or something like that, they'll say, well, I've never come across quartics before. I don't know what a quartic is. So they've kind of completely missed the idea. They don't really know what a polynomial is, for a start. And they're always looking for excuses, for reasons for not doing something. I can't do it because I've not been told about it. I can't do it because I've not been given enough examples with it. This, that, and the other. And the fact of the matter is, nobody cares. Okay? You can make excuses all you want, or you can just get on with it, which is what you need to do in the MAT, which I'm sure many of you, if not all of you watching this, are prepared to do. Okay, if you're preparing for the MAT, then you're probably in that situation where, yeah, you kind of get it. Okay, so without further ado then, let's have a look at the problem that we're presented with here. So there's a few parts to this problem. It's quite a lengthy problem, but there's nothing that's really terribly difficult about it. But I like this problem because you can use a lot of diagrams to justify your reasoning. Okay, so a lot of purists might say, oh, well, you can't use diagrams because you can't draw conclusions from diagrams and things like this. No, you can draw diagrams. You can use diagrams. It's true that you can't draw definitive conclusions from diagrams, but you can use diagrams to great effect to get the ball rolling when it comes to finding a solution to a problem. Even if you think that you're not a very visual person and you insist on, you've got this stubborn insistence on using algebra and shunning diagrams and things like that, you just give diagrams a chance. You might realize that actually you're a bit more of a visual person than you thought. I remember when I was doing A-level maths, yes, I went through a phase where I was kind of thinking diagrams, you shouldn't be using them, they're not worthy, you need to be doing everything using algebra, until I realized that diagrams made things 10 times easier. Okay, why make things more difficult than they already are? Just use diagrams. Okay. Of course, you do need to exercise some caution with diagrams, and there's something that I'm going to slip in here at some point which demonstrates why you need to exercise a little bit of caution. But even though you've got to be careful when you use diagrams, that doesn't mean that you shouldn't be using them, or you can't use them, or that they're too dangerous to use, or anything like that. Just use them. Okay. Right. So a function f of x is said to be even if f of minus x is equal to f of x for all x. Okay, for all x. And a function is said to be odd if f of minus x is equal to minus f of x for all x. This is all we're told about even functions and odd functions. We're not told anything more. We're not told whether they have to be continuous. We're not told whether they can be discontinuous, whether they have to be differentiable, whether they have to be polynomials or any other type of function. We don't know all of this stuff just yet. Now, it might be that there are certain types of functions that are excluded from being even or odd, but we're not going to worry about that right now. We've just got the definitions. We need to make sure that we understand the definitions. So think about them, make sure that you grasp them, because you're going to have to use their properties to use the definition, to figure out the properties, some of the properties. And having the definitions is your start point. It's a sufficient start point, okay? Because then what we're asked to show is that what symmetry does the graph y equals f of x of an even function have? And then correspondingly, what symmetry does the graph y equals f of x of an odd function have? So let's start with the first one. If we've got an even function, what might an even function look like? Okay, so this is x, this is f of x up here. So as we can see, there's kind of a division in these between what we might recognize as positive numbers and negative numbers. Okay, so if I restrict x in the first case to just positive numbers, then this tells me what f is going to look like on the positive value for positive values, including 0. And this bit is going to tell me what f looks like on negative values. Okay, so let's just kind of limit x to positive values, and let's have a think about what my f of x might look like for positive values. Well, it could look like anything, almost anything. There might be some types of functions that are excluded. I can't think of any off the top of my head, but it could literally look like anything. So I'm going to draw something that's not too complicated. So let's go for something like that maybe. Okay, so this is my f of x. So what I'm going to do is I'm going to choose a particular value of x here. And I'm going to go to its corresponding negative over here. Roughly going to be about there. And what this tells me is that the value of the function f at this point is going to be the same as the value of the function at this point. Okay, and not only is it the case at this point, it's also going to be the case at, if I choose this point here, x naught, the value at minus x naught is going to be the same as the value at x naught. If I choose x1, the value at x1 is going to be the same as the value at minus x1. So that tells me then that the graph over here is going to kind of look like this, but reflected in the y-axis. So, okay, that's why I drew something that's not too complicated, but it's still, okay, that'll do. right? So the value at minus x is the same, should look roughly the same as the value at x. I know the lines are not necessarily straight. It doesn't make any difference though. It doesn't matter if your diagram's not perfect, don't worry about it. The value at minus x naught is roughly the same at x naught, and the value at minus x1 is roughly the same as the value at x1. So what kind of symmetry do I have? I've got a reflectional symmetry in the line x equals 0 or the y-axis or whatever. So this is a kind of geometrical argument that I'm using here, which is fine, by the way. This is fine on the MAT to do stuff like this. You're expressing an idea. It's much better for you to express an idea on the MAT, even if it's imperfect, even if it's not fully developed. It doesn't matter. You're expressing a good idea. If you've got good ideas, all of the other stuff can be further developed, you know, with further study, further down the line, once you get to university and all that kind of stuff. The problem is if you don't have any ideas in the first place, okay? If you're just devoid of any original thought, which some people are, by the way. Some people are very good at regurgitating information, and they see that that's all maths is about, just regurgitating information and getting the right answer. But it's not. It's much more than that. It's about having ideas, learning to develop those ideas, learning to express those ideas clearly. And that's what the MAT is giving you an opportunity to do, to express your ideas, to show that you have good ideas, even if at this stage you're not quite able to fully develop the ideas. Don't think that your success in the MAT comes down to purely whether you got the right answer or not. The examiners in your MAT will be much more interested in somebody who has good ideas that are not necessarily fully developed and doesn't necessarily quite get a complete solution to a problem. They'll be much more interested in somebody like that than somebody who's just obviously spewing up kind of rote methods that they don't really even fully understand. Even though they might be getting the right answer, through what they're writing, they will be clearly demonstrating. It is very easy to see this, by the way. It's very easy for somebody who knows what they're looking at to notice this. It will be very easy to see that these people don't know what they're doing, that they've been coached to within an inch of their life, and they're just spewing out things that they don't understand. Don't be that person, okay? And don't worry if you're not getting full and complete solutions to your problems. If you've got some good ideas and you're expressing them, that's what's going to count for a lot more on your MAT. Okay. By the way, if it looks like I keep looking beneath the camera, that's because my computer is here with the question. Okay. So there might also be algebraic methods that you can use. For example, f of minus x equals f of x. This kind of resembles one of the transformations that you might be familiar with. So the transformation f of x replaced with f of minus x. For example, this is a reflection, represents a reflection in the y-axis. Yeah, the y-axis. I had to think for a second there. So you might be able to use that. I'm not saying that this is how you have to do this. Do not, under any circumstances, take what I say in this video or any of my other videos for that matter as model solutions, as representative of some kind of model solution. It's not. All I'm trying to do in these videos is to get through to you the kinds of difficulties that are involved with problem solving, how you might overcome some of those difficulties, some kinds of maybe give you some ideas about things to think about, ideas about techniques that you might not be familiar with, that you might be able to expand on yourself, that you might come to be able to use to great effect further down the line. Okay, so these videos are really just about giving you ideas. I want to pass my information on to you as much as possible, but they're not to be taken as model solutions. If you're after model solutions, look at the mark scheme or something like that, because that's not what I'm interested in. Okay, so how about if we've got an odd function then? What kind of symmetry will the graph have if we've got an odd function? And I'm going to, just to highlight the fact that you've got to be careful when you use diagrams. I'm going to make a little bit of a mistake on this one. Some of you will see it straight away, some of you won't. Don't worry if you don't see it. I will explain it. So let's say we're trying to figure out what a graph of an odd function might look like. Okay, so let's do a similar thing. We've got this kind of division between positive values of x and negative values of x, maybe. So I'm going to concentrate on positive values of x, and I'm going to draw my graph something like that. Okay, and I choose a value x, and I go to its corresponding negative over here, minus x. What I'm expecting then is that, according to this definition, the value of f at this point here is going to be the negative of the value at this point here. But that's going to be true, again, for any value of x, any positive value of x. Okay, and including 0, right? Okay. So, what I'm going to expect to see is something that kind of looks like this. Right? This satisfies this for all x, right? F minus x equals f of x. Or does it? Does it satisfy all of the conditions? It doesn't quite. Now, if you use this diagram, you could still arrive at the correct conclusion, which is that we've got a rotational symmetry about the origin. But you've arrived at the correct conclusion through logically incorrect reasoning. Okay, and this is important. You've got to learn to pick up on stuff like this, and you don't always. Sometimes the logical fallacies that you do insert into your arguments sometimes are very difficult to pick up. But as a mathematician, it's something that you've got to learn to develop and become quite sensitive to these. And even then, it sometimes can be very difficult to see where the holes are in your argument. You know that something's wrong, you're trying to figure it out. Sometimes it can take some real effort to figure that out. But nevertheless, you've got to do it. So what's wrong with this? Well, some of you will probably know already, but I'll just go through it. Let's have a look at what happens around f of 0. So let's say f of 0 is equal to 2, for example. So that, as you're probably aware, 0 is equal to minus 0. But according to this, f of minus x is equal to minus f of x for all x, including 0. So this is going to be equal to minus f of 0, which is equal to minus 2. I don't know about you, but last I heard, 2 minus 2, not equal. Okay? So something's wrong here. And the problem is that there's only one possible value of f of 0, and that's 0. Okay? So f of 0 is equal to 0. Then what we get here is minus 0. 0 minus 0 are obviously equal. But there's no non-zero number that is equal to its negative. Okay, only 0 is equal to its negative, or at least in real number terms, anyway. Okay, so my diagram's a little bit wrong here. That's fine. Sometimes it can take a few iterations for you to get to a diagram that's actually right, that's actually going to work. There's nothing wrong with that. So let's just change this diagram a little bit, so it resembles something that's a bit more accurate. So x, f of x. So we're going to stick with the same kind of shape, but it's going to look something like this. So an odd function, therefore, has to go through the origin. But now what we're seeing is that if we choose x here and minus x here, then what was I going to say? I've lost my train of thought now. Oh, the value of f at minus x is equal to the value at x here. Okay. Okay, so let's... Oh, so what's the type of symmetry? Nearly forgot there. The type of symmetry is a rotational symmetry. About O of 180 degrees, pi radians, whatever. I'm choosing degrees because the rest of the problem involves degrees. Okay, so that's the first bit done. And then moving on to part B. Use these symmetries to show that the derivative of an even function is an odd function and that the derivative of an odd function is an even function. You should not use the chain rule. In other words, don't use differentiation. Okay, so again, there might be various ways that you can go about this. I would probably go for a geometrical argument here, or predominantly geometrical. I'm not saying it's going to be exclusively geometrical, predominantly geometrical. So how is this going to work then? So let's think about the gradient at, say, this point x here. Now, I can try to draw this in. So we draw a tangent line in at x, and we draw a tangent line in at minus x, for example. Not very well drawn. They're supposed to be tangent lines. But by the reflectional symmetry in the line x equals 0, that means that whatever gradient this has, this is going to have the negative gradient of this. Okay, so if this has a gradient of 3, this will have a gradient of minus 3. It has a gradient of 5, this will have a gradient of minus 5. So in other words, what we're seeing is that f primed of minus x is equal to minus f primed of x. Okay, the gradient at minus x is equal to the negative of the gradient at x. Well, that's exactly the definition of an odd function. So the gradient function of an even function is an odd function. Okay, you'd have to explain this in a bit more carefully in your exam. Okay, I can explain things using my voice here via the video. You would have to obviously express your ideas clearly in your exam in writing, and you must do this. Do not just write this somewhere on the page and expect your examiner to know what you mean. Okay, say this fits the definition of an odd function, and therefore the gradient function of an odd blah 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 blah. However you want to express it, but part of your job as a problem solver, as a mathematician, is expressing your ideas clearly. So maths is not about just writing all the symbols on the page. It's about communication as well. Communicating your ideas. If your idea exists only in here, it doesn't exist at all, for all intents and purposes. It only exists when it's in a form that can be communicated. Okay, time for a bit of coffee. By the way, I hope you're finding these videos that I do on MAT and STEP and things like that useful. If you do find them useful and you're finding some benefit, deriving some benefit from them, please hit the subscribe button and hit the like button. I'd be really grateful, because I don't get any money for making these videos. I do not get paid for making these videos in any way, shape or form. And I make these videos because I want to help people prepare for their exams and to make sure that they're as prepared as possible. And I want to continue making these videos, but I'm only going to be prepared to make these videos if there are actually people who are going to benefit from these videos. Because it does take a lot of time, a lot of effort for me to make these videos, go through the problems and everything. So if you do get some benefit from them, please show your support for this channel, because I really do want to continue making these videos. But if there's not anybody that's actually getting any benefit from them, then I might go off and do other things instead. So please show your support, and also share these videos with anybody else that you think might be interested in using them or that might get some benefit from them. That's great. Cheers. So how about this one then? We can do a similar thing here. It's a little bit more difficult. I'm going to give you the idea. I'm not going to go through exactly. I'm just going to give you the idea here though. So maybe if we draw the tangent line in at x there, and we draw the tangent line in at minus x, we might get the idea. That's not a very good tangent line, but you get the idea. We might get the idea that the gradient here at this point is the same as the gradient at this point. That's certainly how it looks from the diagram. How might you justify this? Well, you could think about A rotation about O, maybe you can think about it in different ways. Maybe a reflection in the line in the y-axis, and then followed by a reflection in the x-axis, for example. So that might allow you to deduce that the gradient at this point is going to be equal to the gradient at this point, for example. Because when you reflect in the y-axis, the gradient here would be the negative of the gradient here, but then you reflect in the x-axis, the gradient here is going to be the negative of the gradient here, which is in turn the negative of the gradient here, so therefore they're going to have equal gradients. Something like that, okay? Again, you just got to find a way to express your idea, but what we can see here is that the conclusion that we're driving at is that f primed minus x is equal to f primed x. And again, this is for all x. Now, okay, with this one, it's got a bit of a kink maybe at 0, so maybe there might be an exception when x equals 0, for example, because your even function is not forced to be differentiable at 0. Ignore all stuff like that. That's stuff that you'll worry about, stuff like that, when you get to university and you're doing differentiability and differentiation and things like that. So what you know about differentiation now, based on your A-level studies, is a very small part of differentiation. You'll go into much more detail, and you'll pick out these little difficulties. You'll pick them all out. Okay, so that's it. That's that part done. So we've got that this fits with the definition of an even function. So the derivative of an odd function is an even function. Job done. Okay, so let's have a look at the next part then. So there's quite a bit of information for this part. Well, let's have a look. So I'll put it up on the screen so that you can see it. I will leave a link, by the way, to this past paper in the description to this video so that you can download it. But throughout the video, I have done, hopefully, if I've remembered, and I will do, put the question up on the screen at various points so that you can see the question for yourself. So we've got a diagram as well here, and for minus 45 degrees less than theta less than 45 degrees, the line L makes an angle theta with the line y equals x, as drawn in the figure. Let A of theta denote the area of the triangle which is bounded by the x-axis, the line x plus y equals 1, and the line L. Okay, so let's get all that into a diagram. X plus y equals 1. Y equals x. We've got L. And this is the angle theta here. Oh, theta 1, 0, 1. And this is the area A theta. Okay, A of theta. Okay, so first off, make sure that you're able to interpret this information. So we're told, for example, that 0 is less than theta is, minus 45 is less than theta is less than 45 degrees. So we're working in degrees here. What this means is that if we start with L coinciding with the line y equals x and we rotate in an anti-clockwise direction, then theta increases. And if we start at y equals x again and we rotate in a clockwise direction, then theta will decrease. So here, theta is going to be positive. Here, theta is going to be negative. Okay. Also be aware of how the area A theta is defined. It's the area bounded by the x-axis, the line x plus y equals 1, and the line L. Okay. Just make sure you're clear on this stuff. Otherwise, it's potentially going to make things a little bit more difficult for you further down the line. Okay, so part A. Let 0 less than theta less than 45 degrees, so we're dealing with positive values of theta here. Arguing geometrically, explain why A theta plus A minus theta is equal to a half. Okay, so we're actually being given permission here, explicit permission to argue geometrically. It's kind of indicating the importance of diagrams in your reasoning. Okay, how important diagrams actually are. That you can argue from diagrams. It's just, you can't necessarily derive definitive conclusions, but you can derive certain ideas from them. Okay, so let's have a look anyway. Arguing geometrically. So we've got this big triangle here. So I'm just going to draw it here. 0, 1, 1, and the area of this is equal to a half. Okay, why? Half base times height. Easy, right? Okay, so but this area is made up of two bits, a theta plus some other bit, which we're going to have to figure out. It's not difficult. Now, what it might be worth noticing is that there is a symmetry about the line y equals x in this diagram. It might not look like it from my diagram, but the diagram doesn't have to be drawn perfectly. But what I'm going to do is I'm going to reflect the line L in the line y equals x. Okay, so it's going to look something like this. I call it L primed. So this angle here now between L primed and y equals x is not theta, it's minus theta. It's the same size as theta, same magnitude, but it's opposite in sign because of the way that we're measuring angles here. Okay, so this area, remember the area bounded by the x-axis, the line x plus y equals 1, and the line L primed in this case is going to be a of minus theta. Now, because of the symmetry, the reflectional symmetry in the line y equals x, and do write this stuff in your exam. Don't leave it to your examiner to guess what you mean. Write, there is a reflectional symmetry in the line y equals x. Make it abundantly clear where you're coming up with how you're coming up with your conclusions, where you're deriving your conclusions from. Okay? Don't leave anything to the imagination of your examiner. Well, this area is equal to this area, just by symmetry. But this area is a of minus theta. So this area is equal to a of minus theta. So that's where we get our conclusion from. Obviously, you need to write something. Don't just present this and expect your examiner to know what you're getting at. Spoon feed your idea to them in your reasoning. Okay? Make it very, very clear. Okay, so part B, for 0 less than theta less than 45, determine a formula for a of theta. I'm going to need a new diagram, otherwise this is going to get a bit cluttered, isn't it? So x plus y equals 1. I'm just going to draw L in. I'm not going to bother with y equals x. Okay, so this is a theta, and as you can see, it's just a triangle. Okay, so a of theta is just a triangle. How do you find the area of a triangle? Half base times height. Yeah, half base times height. So, or perpendicular height. So if the base here is 1, so it's going to be half times 1 times, let's say this is x. So the point of intersection here is going to have coordinates x, y equals 1 minus x. So the height of the triangle is going to be 1 minus x. So it's going to be times 1 minus x, which is half 1 minus x. So that's my formula for the area of for a of theta. Actually, no, it's not. Because this suggests that a is a function of theta, not a function of x. Now, it turns out that x can be expressed in terms of theta, in which case I've got to find that expression and replace this, or alternatively just find a different way for finding the area a theta using other means, whatever, okay? Whatever you choose. My preferred option here is to try to express x in terms of theta and then substitute it. And, okay, this angle here is theta plus 45. It's not theta. It's theta plus 45. So we've got a right angled triangle here. Nice right angled triangle, theta plus 45, x, 1 minus x. So what I get is that tan theta plus 45 is equal to, what's it equal to? Opposite over adjacent, 1 minus x over x. So if you rearrange this, you get x tan theta plus 45 equals 1 minus x. So x is equal to 1 over 1 plus tan theta plus 45. So this is equal to a half 1 minus 1 over 1 plus tan theta plus 45. Okay, so that's my formula for A in terms of theta, right? Technically, I guess yes, but if you leave this in this form, you're demonstrating to your examiner one of maybe at least two possibilities. One, you're lazy because this can be simplified, but you've not bothered to simplify it. Or B, you've just not recognized that you can simplify this. Neither of these works in your favor. If you're lazy or if you've just not spotted it, that means you might have problems further down the line. Okay? Mathematicians are lazy in a certain sense, but not when it comes to simplification. So you need to motivate yourself to do some simplification when you see it needs to be done. Obviously, if you don't see that this needs to be simplified, that's a separate issue. That's something else you're going to have to work on. If it's just you can't be bothered to simplify this, then okay, on your head be it if you don't have the success that you're after in the MAT. So yes, do simplify this. So what we're going to get, a half 1 plus, so it's going to be tan theta plus 45 over 1 plus tan theta plus 45. Clear the space here. We're still not done. This is equal to a half. So I'm going to use a trigonometric identity now. Tan theta plus 45 is tan theta plus tan 45 over 1 minus tan theta times tan 45 over, 1 plus tan theta plus 1 over 1 minus tan theta. By doing things like this, you're demonstrating that you understand. You're demonstrating what you are able to do. Again, the MAT is a perfect opportunity for you to demonstrate what you are capable of doing. And if you hold back, if you think, oh, I can't really be bothered to simplify this, that's your problem, okay? There's nothing anybody can do to help you with that other than yourself. You have to be prepared to do what you need to do. So this is a half. Multiply numerator and denominator by 1 minus tan theta. Then I'm going to get tan theta plus 1 over 1 minus tan theta plus tan theta plus 1, which is minus tan theta plus tan theta. 1 plus 1 is 2. It's going to be a quarter tan theta plus 1. Bingo. And that's it, right? How much nicer is that? Plus, what you'll find is that if you don't do this simplification, the next part of the problem is going to be incredibly difficult for you. Now, this idea of simplification is something that a lot of people really resist at A level and GCSE as well, but very much at A level. You know, a question that I'll often get is, oh, if I don't simplify, will I still get my marks? And the answer to that might be, well, you might not lose marks specifically for not simplifying, but you might lose marks because if you don't simplify, you might not be able to see what you need to see in order to do subsequent parts of the problem. Okay, so if you didn't do this simplification, the next part of this question is going to be very difficult for you to do. Okay, this is going to be much easier for you to work with, much easier. Okay, so you might be shooting yourself in the foot by not doing the simplification. These techniques and things that you've been given for simplifying expressions, they haven't just been given to you As they're not an end in themselves, they're a means to an end. They're meant to make your life easier, but for them to make your life easier, you have to choose to use them. Okay, so don't be lazy. It's got a long story short. Right. So the next part is, where are we? Sketch the graph of A of theta against theta for minus 45 degrees, less than theta, less than 45 degrees. Okay. So in other words, we need to sketch the graph of this. So let's write it up here. A of theta is equal to, what is it, a quarter tan theta plus 1. Now this is dead easy, by the way. If you're familiar with transformations of graphs, this is going to be easy. If you're not too hot with your transformations of graphs, then it's just going to be more difficult for you. Okay, so what I see when I see this is a translation of the graph of tan, and then so a translation of 1 unit in the parallel to the y-axis, and then a stretch of scale factor a quarter parallel to the y-axis. Okay, so take it step by step. Okay, take it step by step. Now I know that we don't actually need to go all the way to 90. We only really need to be going to 45. But I'm gonna stick with 90 just for the time being. So what you get is, this is tan. Okay, so we've got the asymptotes here at 90 and minus 90. So tan theta plus 1, right? So maybe now if I go to 45, I know that the value at 45, minus 45 is minus 1. So when I translate the whole thing up, I'm going to get a graph that looks something like this. So that's going to be at 45. So it's going to be 0 here. It's going to cross the y-axis at 1, and it's going to have a maximum here at 2, or it's going to tend towards a maximum at 2. But then I've got the stretch scale factor a quarter to deal with, so my graph is going to look more like, it's going to have roughly the same shape. I'm not going to bother redrawing it in. It's going to go through a quarter on the vertical axis and half up here. Okay, so my graph is this thing here. Okay, so it's at minus 45. 45 crosses the y-axis, or the vertical axis at a quarter, and this point here is going to have coordinates 45 degrees, a half, even though these endpoints are not included because of the range of possible values of theta. This is the theta axis. Okay. If you wanted to draw separate diagrams, so this is a bit scrappy now because it's got all of my working on. Don't necessarily cross it out, but if you want to draw a separate diagram that makes it clear what the graph of this looks like specifically, then do so. Again, don't cut corners. So let's have a look at the next part. So part D, in light of the identity in part 2a, what symmetry does the graph of a theta have? Okay, so the identity that we proved was that a of theta plus a of minus, sorry, let me get it right. A of minus theta is equal to a half. Okay, so what I'm expecting is that this is going to have something to do with an odd function. Okay, you can kind of see that this almost resembles an odd function, but what's the problem here? It doesn't go through the origin. Okay, so maybe if this was translated by a quarter, it would go through the origin, right? And then we'd have, and hopefully we'd be able to show that we've got an odd function. Maybe I can do that. Maybe I can do that. So let's say we've got a of theta. If I just kind of rearrange this, then I get a of theta minus a quarter is equal to minus a, minus theta, minus a of minus theta plus a quarter. Okay, so let's say this is f of theta, right? So we've got f of theta is equal to a of theta minus a quarter. So in other words, f of theta is a translation of a of theta. Okay, bear that in mind. And minus f of theta is going to be equal to minus a of theta plus a quarter, which is equal to, so minus this is going to be equal to, a of minus theta minus a quarter, right? So minus a of theta plus a quarter is the negative of this, which is equal to, if I multiply this by minus 1, I get this. But that's just equal to what? F of minus theta. So f of minus theta is equal to minus f of theta. So f is an odd function. F is an odd function. But remember that f was a translation of a. So if f is an odd function and it's got a rotational symmetry 180 degrees about the origin, a will have been a translation of f. So a of theta is equal to f of theta plus a quarter. Then a will have a rotational symmetry also, but not around the origin, around 0 a quarter. So a of theta has a rotational symmetry of 180 degrees about 0 a quarter. So a of theta itself is not an odd function, but it's closely related to an odd function. Okay, it's a translate of an odd function. Okay, so then we're on to the final part. Without explicitly differentiating, explain why d2a by d theta squared equals 0 when theta equals 0. In other words, we've got a second derivative is equal to 0. That corresponds to, it looks like we've got a kind of point of inflection here, but it's not a turning point, right? So what I'm expecting here, because tan doesn't have a turning point at 0, its gradient is non-zero at theta equals 0. So what I'm expecting here is to, because the second if this was a turning point, the second derivative equals 0 wouldn't necessarily correspond to a point of inflection. But because I'm expecting the gradient here to be non-zero, the second derivative equals 0 points to a point of inflection, or it implies a point of inflection. So how can we show this without explicitly differentiating, importantly? So you kind of got to have a bit of an idea about the graphs, I guess. How to think about, interpret graphs and things like that. Okay, so let's get rid of this stuff. Okay, so what might we do here? So rotational symmetry, if we need to use that. So could I draw a graph of the gradient? So I'm going to use the diagram. Maybe there's a way that you can do this a bit more algebraically, but I'm going to use the diagram. So what we can see, because we've got the rotational symmetry about a quarter, what that means is that we can see that the gradient of the graph is positive. The gradient is positive, and it's going to hit a certain value here at 0. Okay, it's still going to be positive though. So what we're going to get is positive and decreasing. And then what happens? The gradient changes. By symmetry, if the gradient is positive and decreasing into that point, then coming out of that point, the gradient is going to be positive and increasing. So what does that mean? I've got a turning point. I've got a turning point on the graph of dA by d theta. I've got a turning point on the graph of dA by d theta when theta equals 0. Notice I do not have a turning point on this graph. The turning point is on the graph of the gradient function. So what does that mean? Well, if there's a turning point on the graph of the gradient function, that means that the gradient of the gradient function must be 0 at that point. So i.e. d by d theta of dA by d theta is equal to 0 at theta equals 0. But this is exactly d2a by d theta squared. d2a by d theta squared equals 0 at theta equals 0. This is the definition of the second derivative of a function, by the way. I have got another video up on my channel which goes through second derivatives, third derivatives, and things like this, and how to interpret them in the second derivative test. If you're not familiar with this definition, make yourself familiar with it. Okay, the second derivative of a function is defined to be the derivative of the first derivative, right? So we can understand this as the second derivative of this function, or we can understand it as the first derivative of this function, which means that if I've got a turning point on the graph of the gradient function, the gradient of the gradient function is equal to 0 at that point. Okay, the second derivative. So have a look at that video if you need to. It goes in into more detail. So that's it. Okay. Again, you'd have to find a suitable way to explain all of this stuff. But that brings us to the end of this problem. Hopefully you've found it useful. Like I said, this is not meant to be a model solution to this. It's really just me giving some ideas. Now I do have some notes here. I have solved the problem already, and I've kind of got some notes here. But a lot of the stuff that I've been doing I've been working it out as I've been going along in the video. You might have kind of noticed a little bit. Because I really want to get across in these videos the difficulties that you encounter when it comes to solving problems and the things that you have to think about. You have to give yourself the time and the space to think in order to solve a problem. Don't expect something, you look at a problem that the solution should just pop out of nowhere and you should just effortlessly write out your answer to every single problem. It doesn't work like that. So hopefully you found something useful with this video. That brings us to the end of this problem. If you do have any comments, anything that you would like to say, leave it in the comments section. And with that, I will say thank you for watching this video, and I'll see you in the next video.